In nature, power is rarely measured by numbers. A single organism, perfectly designed by evolution, can dominate an entire ecological chain without ever needing to prove its strength. True power in the wild is quiet. It is efficient, it is restrained. Yet human curiosity has a habit of asking the wrong questions. We look at nature and immediately ask who would win. Bigger or smaller? Faster or slower? Stronger or weaker? But nature does not operate inside arenas. It operates inside limits. The king cobra is the largest venomous snake on Earth, a predator so specialized that it feeds almost exclusively on other snakes. Calm, intelligent, and remarkably controlled, it represents one of evolution's most refined designs. Now imagine placing this apex specialist into a landscape dominated not by large enemies, but by hundreds of venomous arthropods. Scorpions, ancient survivors whose lineage predates dinosaurs, small, numerous, armed with venom, not for conquest, but for survival. At first glance, the image feels dramatic. One giant predator surrounded by 500 venomous organisms. But this is not a story about combat. There is no staged confrontation here. No artificial battle. No cinematic clash of fangs and stingers. What we are exploring is far more interesting and far more real. This is a biological question, a thought experiment rooted in physiology, chemistry, and evolutionary logic. Can the world's largest venomous snake survive sustained exposure to hundreds of venomous arthropods? Not through dominance, not through aggression, but through biology itself. Venom, in nature, is not a weapon in the human sense. It is a communication system, a chemical message designed to interrupt nerve signals, slow muscles, or discourage pursuit. Every venom has limits. Every organism has thresholds. Survival is determined not by how much venom exists in an environment, but by how that venom is delivered, absorbed, metabolized, and neutralized. Numbers alone mean nothing if biology does not cooperate. This is why this question matters, not because it imagines a fight, but because it forces us to understand overlap. What happens when two different venom systems intersect? One optimized for deep injection and rapid neurological shutdown. The other optimized for shallow delivery and immediate deterrence. What happens when tolerance meets exposure? When metabolism meets repetition? When stress meets endurance? To answer this, we must strip away spectacle and focus on reality. We must understand the king cobra not as a monster, but as a biological system. We must understand scorpions not as attackers, but as defensive engineers. Only then can we see what survival truly means in the wild. To answer this question, we must first understand both sides of the equation. The king cobra, scientifically known as Ophiophagus hana, is not simply a large snake. It is a specialist, refined by evolution, for a role that very few predators can occupy. While many snakes rely on opportunistic feeding, the king cobra follows a narrow and demanding path. It feeds primarily on other snakes, venomous or non-venomous, fast or slow, aggressive or cautious. This diet alone reshapes everything about its biology. Its nervous system, its metabolism, its behavior, and even the way it perceives risk are all calibrated for encounters with dangerous prey. A predator that regularly hunts other venomous animals cannot survive on brute force. It survives through control. Physically, the king cobra is imposing. Adults commonly exceed 4 meters in length, with some individuals approaching 5.5. Yet size is not its defining feature. What truly separates the king cobra from other snakes is neurological efficiency. Its brain, relative to body size, is more developed than that of most serpents. This translates into learning, memory, and behavioral flexibility. King cobras recognize territory. They remember escape routes. They adjust strategies based on prior encounters. In the wild, this intelligence reduces unnecessary energy expenditure and minimizes injury. A king cobra that wastes venom or engages recklessly does not survive long. Its venom system reflects this precision. King cobra venom is primarily neurotoxic, designed to interrupt communication between nerves and muscles. When delivered effectively, it causes rapid paralysis and respiratory failure in prey. But venom production is metabolically expensive. Synthesizing complex proteins requires energy, time, and biological resources. As a result, king cobras are selective. They do not inject maximum venom with every bite. They regulate dosage. This ability to meter venom output is critical to understanding their survival strategy. Venom is not a reflex, it is a calculated investment. Equally important is what the king cobra is not. It is not reckless. It is not constantly aggressive. Despite its reputation, most encounters with king cobras in nature involve avoidance rather than confrontation. When threatened, a king cobra will often raise its body, expand its hood, and display rather than strike. This display is not about intimidation alone. It is about information. Size, posture, and visibility communicate risk. Many potential threats retreat long before physical contact occurs. Survival, once again, is achieved without violence. Metabolically, the king cobra operates with remarkable efficiency. As a reptile, it has a slower baseline metabolism than mammals. This allows it to endure long periods without food, reduces oxygen demand, and limits the buildup of metabolic waste. In high-stress situations, this metabolic profile becomes an advantage. Where a mammal might rapidly exhaust itself, a reptile conserves energy. Heart rate increases modestly. Oxygen consumption remains controlled. Stress hormones rise, but not explosively. This matters when considering prolonged exposure to hostile environments. However, there is a critical misconception that must be addressed. King cobras are not universally immune to venom. This idea is often exaggerated. What they possess is selective tolerance through evolutionary exposure to snake venom, particularly neurotoxins similar to their own. King cobras have developed partial resistance to certain venom components. Their acetylcholine receptors, sodium channels, and neuromuscular junctions show reduced sensitivity to specific toxins. But this tolerance is not absolute. It does not extend to all venom types. It does not guarantee survival under unlimited exposure. Biology never offers absolutes. This distinction is essential. Immunity implies invulnerability. Tolerance implies thresholds. A king cobra can withstand small or moderate doses of certain venoms without catastrophic effect, especially when exposure is spaced out and delivered inefficiently. But overwhelming exposure, delivered effectively into the bloodstream, would still pose a serious risk. The question, then, is not whether venom can harm a king cobra. The question is, under what conditions that harm becomes biologically meaningful. Behavior provides another layer of protection. King cobras are acutely sensitive to vibration. Through their jawbones and body contact with the ground, they detect movement with extraordinary precision. This sensory input allows them to assess environments before committing their bodies to them. Areas with dense arthropod activity, irregular vibrations, or unstable substrates are often avoided. This is not fear, it is calculation. Evolution favors organisms that recognize when the cost of engagement outweighs the benefit. Calmness is perhaps the king cobra's most underestimated trait. In stressful conditions, panic is deadly. Panic accelerates metabolism, increases oxygen debt, and amplifies toxin distribution through faster circulation. The king cobra's relatively composed response to threat limits these effects. By remaining still, withdrawing slowly, or repositioning deliberately, it prevents physiological cascades that could turn minor exposure into major damage. Stillness, in this context, is not passivity, it is regulation. All of these traits together paint a clear picture. The king cobra is not a brute force apex predator. It is a specialist built for precision, restraint, and efficiency. Its venom is powerful, but its real strength lies in control. Control over energy. Control over behavior. Control over when to engage and when to withdraw. This raises the central tension of our question. If the king cobra is not immune, if its survival depends on thresholds and restraint, what actually protects it when venomous organisms surround it in large numbers? If size alone is not the answer, and immunity is incomplete, then survival must come from somewhere else. Scorpions represent a completely different philosophy of survival. Where the king cobra embodies specialization and restraint, scorpions embody persistence and deterrence. They are among the oldest venomous lineages on Earth, with fossil records dating back more than 400 million years. Long before snakes evolved, scorpions were already refining their chemical defenses. Their success is not based on dominance or size. It is based on survival under pressure. A scorpion is not designed to overpower large prey. Its venom exists for one primary reason: rapid immobilization or immediate discouragement. In predatory situations, venom is used sparingly to subdue insects or small vertebrates. In defensive situations, venom becomes a warning system. Pain, shock, and neurological disruption are the message. Most animals that survive a scorpion sting remember it. That memory alone reduces future conflict. From a biochemical perspective, scorpion venom is complex but limited in volume. Each scorpion carries a small venom reserve, often measured in fractions of a milligram. Producing venom is metabolically expensive, even for arthropods. A single sting represents a meaningful investment of resources. As a result, scorpions do not sting indiscriminately. They assess threat level. Many defensive stings are dry, delivering little or no venom. Others involve partial envenomation. Full venom discharge is reserved for extreme situations. The neurotoxins within scorpion venom primarily target sodium and potassium channels in nerve cells. By disrupting these channels, the venom causes intense pain, muscle spasms, and in some species, temporary paralysis. In small animals, this effect can be fatal. In larger animals, it is usually non-lethal, but highly aversive. This distinction is crucial. Scorpion venom is optimized to deter, not to kill large predators outright. Delivery mechanics further limit scorpion effectiveness against large organisms. A scorpion stinger is designed for shallow penetration. It must pierce soft tissue to deliver venom effectively. Thick skin, scales, or keratinized surfaces reduce penetration depth dramatically. Even when penetration occurs, venom is often deposited superficially, diffusing slowly through tissue rather than entering the bloodstream directly. This drastically reduces systemic impact. Now consider the illusion created by numbers. 500 scorpions sounds overwhelming, but biology does not add 500 scorpions do not equal 500 effective stings. Many scorpions would never make contact. Others would sting defensively once and retreat. Some would exhaust their venom supply early. Coordination does not exist. Scorpions do not swarm with intent. They do not sacrifice themselves for a collective outcome. Each individual operates independently, driven by immediate survival, not strategy. There is also the matter of risk. For a scorpion, engaging a large predator is dangerous. A single misplaced sting attempt can result in death. Crushing force, body mass, or simple accidental contact can end the scorpion's life instantly. Evolution does not favor suicidal behavior. When given the option, scorpions retreat, hide, or remain motionless. Venom is a last resort, not a primary tactic. Metabolically, repeated stinging is costly. After venom discharge, replenishment can take days or weeks depending on species and environmental conditions. A scorpion that empties its venom gland becomes vulnerable. This biological reality discourages repeated attacks. Numbers lose meaning when each unit has strict physiological limits. This reframes the scenario entirely. The presence of many scorpions does not guarantee sustained envenomation, it guarantees uncertainty. Some stings might occur, most would not, and even those that do occur would be limited in dose, depth, and systemic reach. Venom, once again, only matters if it reaches the bloodstream in sufficient quantity. Without effective delivery, even potent toxins remain localized irritants rather than lethal agents. So the question shifts. If scorpions are ancient, venomous, and numerous, yet constrained by delivery, cost, and behavior, then numbers alone cannot explain danger. The threat must come from somewhere else. Not from venom accumulation, but from something more subtle. Something tied to stress, endurance, and biological limits rather than chemistry alone. And that is where the comparison begins to collapse. At this point, the scenario begins to reveal its central flaw. Comparing snake venom to scorpion venom, as if they operate on the same biological rules, is misleading. These two systems evolved to solve different problems. Under different constraints, using entirely different delivery physics, venom is not just about toxicity. It is about how, where, and how fast that toxicity enters the body. Snake venom is engineered for deep delivery. When a king cobra bites, its fangs act like hypodermic needles. Venom is injected under pressure directly into muscle tissue, close to major blood vessels. From there, it disperses rapidly through the circulatory system. This is why snake venom acts quickly and systemically. The body does not have time to localize or compartmentalize the toxin. The damage spreads before defensive processes can respond. Scorpion venom follows a different path. The stinger delivers venom shallowly, often into the skin or just beneath it. There is no injection pressure comparable to a snake's bite. The venom diffuses slowly through surrounding tissue, encountering cellular barriers, fat layers, and immune responses along the way. Much of its effect remains localized. Pain receptors fire, muscles spasm near the sting site. Systemic spread is limited unless the victim is very small or particularly sensitive. Volume matters as well. A single king cobra bite can deliver tens of milligrams of venom in one controlled injection. A scorpion's venom yield is tiny by comparison. Even across multiple stings, the cumulative volume rarely approaches that of a single snake in venom. Biology does not simply add small doses together and produce the same result as one large dose. Distribution, timing, and metabolism interrupt that arithmetic. Protein complexity further separates these systems. Snake venom contains large, complex proteins designed to disrupt multiple physiological systems at once. Scorpion venom, while potent, is more narrowly focused, often targeting specific ion channels. This specialization makes it extremely effective against small prey, but less devastating against large organisms with slower metabolisms and greater tissue mass. Neutralization speed is another critical factor. Reptiles, including snakes, metabolize and neutralize toxins differently than mammals. Their slower circulation and lower metabolic rates reduce the speed at which venom spreads. This gives their bodies more time to isolate and process toxins. What might overwhelm a mammal quickly can remain manageable for a reptile, especially when exposure occurs in small, repeated doses rather than a single massive injection. Stress physiology complicates the picture further. When an animal panics, heart rate increases, blood vessels dilate, and circulation accelerates. This allows toxins to spread faster. But reptiles do not exhibit the same explosive stress response as mammals. Their hormonal systems respond more slowly. This blunted response limits rapid venom uptake. Remaining still or moving deliberately can significantly reduce systemic absorption. Repeated low-dose exposure often fails not because venom is weak, but because the body adapts. Detoxification pathways upregulate immune responses activate locally. Venom components break down before reaching critical concentrations. This is not immunity. It is tolerance interacting with delivery limitations. Without efficient access to the bloodstream, venom loses much of its threat. This leads to the central insight. Quantity does not override delivery physics. 500 shallow, inefficient exposures do not equal 1 deep, precise injection. Biology respects pathways, not intentions. Venom must reach the right place, at the right concentration, within the right time frame. Without that alignment, even potent toxins fail to produce catastrophic outcomes. So, when imagining a king cobra surrounded by scorpions, the danger does not come from venom chemistry alone. It comes from secondary effects: stress, fatigue, dehydration, injury. The chemistry itself is constrained by physics and physiology. Venom versus venom is not a symmetrical comparison. It is a mishmash of systems designed for entirely different ecological roles. The real threat, if one exists at all, lies beyond the toxins themselves. If venom is not the decisive factor, then the question shifts to something far more fundamental. Survival is not determined by chemistry alone. It is determined by how a body manages stress over time. In prolonged hostile environments, organisms rarely fail because of a single lethal event. They fail because regulatory systems begin to break down. Energy drains faster than it can be restored. Water is lost. Muscles fatigue. Injuries accumulate. This is where real danger emerges. A king cobra would not collapse under venom overload from scorpions. That scenario does not align with biological reality. What could threaten it is sustained stress without recovery. Stress activates hormonal pathways that increase energy consumption. Muscles remain tense. Heart rate elevates modestly. Breathing becomes more frequent. Over time, these changes create metabolic debt. Even efficient systems have limits. Reptiles are remarkably tolerant of scarcity. A king cobra can go weeks without feeding. Its metabolism slows. Energy is conserved, but hydration is different. Water loss through respiration, movement, and environmental heat cannot be ignored. In a dry or exposed environment, dehydration becomes a genuine risk. Fatigue follows. Muscles lose efficiency. Reaction times slow. This is not dramatic. It is gradual. And gradual failures are the most dangerous because they are harder to detect. Heat regulation plays a critical role here. King cobras rely on external temperatures to regulate their body functions. In warm conditions, their muscles perform optimally. In cooler conditions, movement slows. In excessively hot environments, overheating becomes a threat. Prolonged stress increases internal heat production. Without opportunities to retreat to shade or cooler ground, physiological strain increases. Scorpions, by contrast, are masters of heat tolerance. Many species thrive in extreme temperatures and remain active when larger animals must withdraw. Oxygen debt is another factor. Sustained alertness requires continuous oxygen delivery to muscles and the brain. While reptiles manage oxygen efficiently, constant vigilance without rest creates imbalance. Remaining coiled, elevated, or partially upright for long periods consumes energy. Over time, posture itself becomes costly. This is why predators do not maintain threat displays indefinitely. Displays are temporary solutions, not sustainable states. Injury, even minor injury, compounds these stresses. A shallow sting that does not deliver lethal venom can still cause localized pain, swelling, or muscle spasms. Individually, these effects are manageable. Collectively, they interfere with movement. A stiffened muscle slows escape. A painful contact point alters posture. Each small impairment increases energy cost. Survival becomes less efficient. Yet even here, reality intervenes. Scorpions do not pursue relentlessly. They are not endurance attackers. After a sting, most retreat immediately. They conserve energy. They avoid risk. They do not chase. A king cobra is not facing a continuous assault. It is facing intermittent encounters separated by moments of stillness, withdrawal, and repositioning. Behavioral asymmetry is crucial. The king cobra experiences stress from vigilance. Scorpions experience stress from proximity to a large predator. Both systems seek resolution through disengagement. Over time, the environment itself begins to resolve the situation. Vibrations disperse scorpions. Heat gradients draw them into shelter. Open space encourages withdrawal. Nature actively dismantles prolonged conflict. There is also a misconception about coordination. 500 scorpions do not act as a unit. They do not synchronize behavior. They do not escalate collectively. Each individual responds independently to immediate stimuli. This fragmentation prevents cumulative pressure. While one scorpion stings and retreats, dozens remain hidden. Others freeze. Many never interact at all. The environment dilutes threat density naturally. The king cobra's endurance strategy aligns with this reality. It does not attempt to dominate the space. It seeks exit routes, elevation, vegetation, open ground. Survival favors movement away from unfavorable microhabitats. Predators that linger where conditions are hostile waste energy and invite failure. Those that leave survive. This reveals an important truth. Biological limits exist. but they are rarely tested to collapse. Nature avoids extremes. Systems evolve to disengage before failure occurs. Stress builds, signals, trigger withdrawal, and survival continues elsewhere. The king cobra does not need to withstand endless pressure. It only needs to recognize when conditions are inefficient. Survival, in this context, is not heroic, it is practical. It is the quiet decision to leave before costs outweigh benefits. And that decision is written into the nervous system itself. When speculation is stripped away, what remains is ecology. Not imagination, not confrontation, but patterns that repeat across landscapes, species, and time. In nature, prolonged hostile encounters are rare, not because animals lack weapons, but because environments are structured to prevent them. Survival depends on movement, spacing, and avoidance long before danger escalates. A king cobra entering a scorpion-rich environment would not experience sudden immersion into chaos. It would detect the environment before full contact occurs. Vibrations transmitted through the ground would register immediately. Irregular, rapid micromovements signal arthropod activity. The cobra's body, in contact with the substrate, functions like a biological seismograph. This sensory input alters behavior almost instantly. The first response is hesitation, not aggression. The cobra slows. It raises part of its body to reduce contact with the ground. It samples the air. Chemical cues, while limited for scorpion detection, still contribute contextual information. The environment feels inefficient. Movement becomes deliberate. Energy expenditure is minimized. This alone reduces exposure dramatically. Scorpions respond just as predictably. Large continuous vibrations signal danger. Most species are ambush predators or satan-weight defenders. When threatened by a large animal, they do not advance. They disperse, they seek cover. Rocks, crevices, soil, and vegetation become immediate refuges. Remaining exposed increases mortality. Evolution selects for disappearance, not confrontation. This dynamic rapidly breaks the imagined scenario. Instead of a sustained overlap between predator and hundreds of venomous organisms, the environment fragments contact into isolated, brief interactions. One sting may occur. Another might follow minutes later. But continuous exposure does not materialize. The landscape itself interrupts it. Elevation plays a key role. King cobras are capable climbers. They utilize fallen logs, roots, rocks, and low vegetation to lift portions of their body away from the ground. This reduces contact surface area. Less contact means fewer opportunities for stings. Even partial elevation changes the entire risk profile. Withdrawal follows naturally. Predators do not commit to spaces that offer no reward. Scorpions are not prey for king cobras. There is no incentive to remain. Without food motivation, endurance gives way to relocation. A few meters can completely change the encounter landscape. Scorpion density drops. Microhabitats shift. The threat dissolves. Time further favors disengagement. Scorpions are largely nocturnal. Activity peaks at specific temperatures and humidity levels. As conditions change, movement decreases. A king cobra that waits, even briefly, benefits from declining encounter rates. Patience once again becomes a survival mechanism. From an ecological standpoint, this is the rule, not the exception. Predators pass through hostile microhabitats without remaining in them. Prey and defensive species avoid large predators without pursuing them. Conflict is resolved through spatial separation, not escalation. This is why ecosystems persist. Constant confrontation would be unsustainable. The idea of a predator surrounded indefinitely by hundreds of venomous organisms assumes a static environment. Nature is not static. Temperature shifts, light changes, wind moves, scent, vibrations fade. Every variable pushes organisms toward disengagement. The longer time passes, the less likely interaction becomes. This explains why there are no documented cases of mass envenomation involving large reptiles and arthropods in natural settings. Not because it is impossible in theory, but because ecology prevents it in practice. Systems designed for survival avoid configurations that threaten stability. The king cobra survives not by enduring impossible odds, but by never allowing those odds to exist. It enters, assesses, adjusts, and leaves. Scorpions do the same. Both systems succeed because neither seeks prolonged contact. Nature resolves conflict long before violence occurs. At this stage, the original question begins to feel misplaced. Not because it lacks drama, but because it misunderstands how nature defines success. Humans instinctively frame the natural world as a series of contests. Who is stronger? Who is faster? Who would win? This mindset comes from arenas, not ecosystems. In nature, survival is not awarded to the last organism standing. It is awarded to the organism that never needed to stand at all. The idea of victory implies dominance. Dominance implies prolonged confrontation. Prolonged confrontation implies wasted energy and elevated risk. None of these are compatible with long-term survival. Apex predators do not remain apex by constantly proving power. They remain apex by avoiding unnecessary costs. Every injury, every spike in stress, every inefficient encounter reduces future survival probability. Evolution selects against spectacle. The king cobra exemplifies this principle. Its status as an apex predator does not come from overpowering everything it encounters. It comes from precision. It hunts selectively, it avoids conflict when food is absent, it displays rather than strikes, it withdraws rather than escalates. These behaviors are not signs of weakness. They are markers of optimization. An animal that survives decades in the wild is one that has learned restraint. Scorpions follow the same logic from the opposite end of the size spectrum. Their venom is not a declaration of dominance. It is a boundary, a signal that says, do not proceed. Pain is cheaper than pursuit. Deterrence is cheaper than combat. A scorpion that survives does so by making itself unpleasant to touch, not by killing everything that touches it. This strategy works precisely because it discourages further interaction. When these two systems meet, neither is seeking victory. The king cobra is not hunting scorpions. The scorpions are not attacking the cobra. Each interaction is accidental, defensive, and brief. Asking who wins ignores the fact that neither participant is playing the same game. One is optimizing for precision predation. The other is optimizing for survival through deterrence. Their objectives do not overlap. This is why ecosystems are stable. If animals behaved the way humans imagine them behaving, constantly testing dominance, ecosystems would collapse under the weight of wasted energy and injury. Instead, natural systems minimize conflict. They resolve overlap through spacing, timing, and avoidance. Predators pass through. Defensive species retreat. Encounters end without conclusion because conclusion is unnecessary. The who won framing also ignores scale. Survival is not measured in moments, but in years. A king cobra that leaves an environment intact has won by default. A scorpion that avoids being crushed has also won. There is no scoreboard. There is only continuation. Life persists by reducing exposure to risk, not by conquering it. This reframing changes how we interpret the original premise. The dramatic image of a single predator surrounded by hundreds of venomous organisms is compelling, but misleading. It suggests inevitability. It suggests escalation. In reality, nature resists both. The longer an encounter lasts, the more likely it is to dissolve rather than intensify. Victory, in ecological terms, is absence of damage. It is energy conserved, it is injury avoided. It is relocation rather than confrontation. Both the king cobra and the scorpions are masters of this logic. Their coexistence in overlapping habitats is proof that survival does not require dominance. The real survivor is the one who never needs to fight. When all layers are assembled, the question resolves itself without drama, not because it lacks tension, but because biology removes the need for resolution. The king cobra and the scorpions represent two highly refined survival systems that evolved for entirely different purposes. Each succeeds precisely because it avoids situations where its limits would be tested to failure. The king cobra is optimized for precision. Its body is built for controlled movement, efficient metabolism, and deliberate engagement. Its venom is powerful but selectively used. Its intelligence reduces waste. Its behavior minimizes risk. Everything about its design favors patience over aggression. In an environment that offers no prey and elevated cost, the system does not push forward, it disengages. Scorpions are optimized for deterrence. Their venom is not a tool of domination, but a boundary mechanism. Pain, shock, and memory are the currency they trade in. Their small size and limited venom reserves make prolonged engagement inefficient. Retreat, concealment, and stillness preserve survival. Their strength lies in discouraging contact, not sustaining it. When these systems intersect, there is no escalation curve. There is no biological pathway that leads toward a mass envenomation scenario. Venom delivery is inefficient. Exposure is fragmented. Stress signals trigger withdrawal. Environmental variables dismantle overlap. Time dissolves interaction density. The premise collapses under ecological logic. There is no realistic situation in which hundreds of scorpions repeatedly and effectively envenom a king cobra to lethal effect. Not because scorpions are weak, and not because the king cobra is invulnerable, but because nature prevents such configurations from persisting. Biology is not reckless, it is conservative, it builds exits into every system. This synthesis reveals the deeper truth behind the illusion of conflict. Survival does not reward excess, it rewards balance. Systems that escalate unnecessarily disappear over evolutionary time. Systems that disengage endure. The king cobra survives by knowing when not to advance. Scorpions survive by ensuring they are not worth touching. There is no winner because there is no contest. Only two designs, each complete within its ecological role, each avoiding the conditions that would force a verdict. In nature, resolution does not arrive through conquest. It arrives through separation. This is the answer hidden behind the title. Not a battle, not a survivor crowned over another, but a demonstration of how perfectly nature engineers restraint. In the wild, survival is rarely decided by numbers, strength, or even venom. Those are the details that capture attention, not the forces that sustain life. What truly governs survival is design. Design that limits exposure. Design that favors restraint. Design that knows when to disappear. The image of conflict is powerful because it simplifies nature into something familiar. A winner, a loser, a moment of impact. But ecosystems do not operate on moments. They operate on continuity. Life persists not through constant confrontation, but through the quiet avoidance of unnecessary risk. Every species that exists today is here because it learned, over millions of years, how not to fight. The king cobra does not survive because it can overpower everything around it. It survives because it does not try to. Its intelligence, patience, and metabolic control allow it to move through the world selectively. It leaves environments that offer no reward. It avoids conditions that amplify costs. It conserves energy not as a strategy, but as a default state. Scorpions survive for the same reason, expressed differently. Their venom draws invisible boundaries. It teaches predators that contact is expensive. They do not chase. They do not escalate. They wait, they deter, and they retreat. Their success is written not in the bodies they kill, but in the interactions they prevent. This is why the question of who survives dissolves when examined closely. Survival was never at risk. The systems involved were never designed to collide indefinitely. Nature resolves conflict long before it needs to test limits. Space, time, temperature, and behavior intervene. The environment itself becomes the mediator. Understanding this changes how we see the natural world. Predators are not reckless. Venom is not gratuitous. Danger exists, but it is carefully managed. What appears violent on the surface is beneath it, a network of decisions designed to preserve stability. Nature is not cruel, it is precise. The illusion of conflict is compelling because it mirrors human storytelling, but the truth is quieter and far more powerful. Life survives not by winning battles, but by avoiding them, not by overwhelming opposition, but by recognizing when to move away. This is the lesson hidden behind the question. In nature, the greatest strength is knowing when not to stay. The greatest victory is leaving without harm, and the greatest design is the one that never needs a fight to prove its perfection. If you want to understand the natural world, do not ask who wins, ask how life continues.